Okay, hello everyone. Thank you for joining this week's BDPA Tech and Career Talk. As a reminder, I have muted the lines at this time. I will unmute them as we get into the Q&A portion later on in the call. If you are using the app or the desktop version, the chat window is available. And you can put your questions or comments in the chat if you don't want to forget about them. Then we will make sure they get asked once we get to the Q&A portion of the call. So for today, this is our BDPA Tech and Career Talk, and if it is your first time joining, we have these twice a month on the second and fourth Friday of the month. We have a number of different speakers come in and speak on a range of topics as it relates to the IT technology field. So today we are glad to have Chris Crawford with us from the University of Alabama, and I'll get into a brief introduction of him shortly. But for those who may be unfamiliar with BDPA, BDPA is Black Data Processing Associates. The organization was started in 1975 as a way to train youth up with computer programming skills, but also provide a forum for IT professionals to build their skills and continue to thrive in the IT industry. So that's a little bit about BDPA. I'm Devin Jenkins. I work with GE Healthcare here in Milwaukee in our supply chain digital technology organization as a senior technical product manager, and I facilitate these calls each month. So that's a little bit about me, a little bit about BDPA. Let's move into a quick intro of Chris, and while I'm doing that, Chris, I'm going to go ahead and give you the presenter rights so you can get your presentation up and going. So you should see that request coming over. All right, good.
See my, I guess, initial slide.
Yeah, we see your slide up.
Okay, great.
Okay. I'm going to mute you shortly, Chris, because I'm catching that echo.
All right.
All right, so we have Dr. Chris Crawford with us today, who is an assistant professor at the University of Alabama in the Department of Computer Science. He directs the Human Technology Interaction Lab. Prior to joining University of Alabama, he obtained a PhD in human-centered computing from the University of Florida. And prior to that, he had his Bachelor's of Science degree in computer science from the University of Alabama. His research focuses on human-robot interaction and brain-computer interfaces. He has investigated systems that provide computer applications and robots with information about a user's cognitive state. Previously, he developed the world's first brain drone racing system. So interesting there. I look forward to hearing about that, hopefully. Dr. Crawford also recently developed Neuroblock, which is a software platform for developing neurofeedback applications. His work has been featured on over 800 news outlets, including Discovery, USA Today, New York Times, and Forbes. So well-credentialed brother here. Excited to hear what he has to share with us today. This should be a pretty interesting topic. So without further ado, I'll turn it over to Chris.
All right, thank you for the great introduction. Thank you for the invitation as well. I look forward to sharing our perspective, ours as in the Human Technology Interaction Lab perspective of brain-computer interfacing. And so in this talk in general, what I hope to do is to introduce everyone to kind of some of the basic and fundamental concepts of brain-computer interfacing. And also I'll talk a little bit about my previous work on brain-robot interaction. And then I will pivot toward talking about some of the more recent things that we have recently started to explore, thanks to some support from the National Science Foundation. So before I get started, I guess a little bit about myself. When I'm not engaging with robots, as you see here in this top photo, or using brain-computer interfaces to tweak around, to figure out certain types of innovations. I like to farm, so over here is my little farm on the left side. I'm originally from Alabama, and so I'm from this little small dot here called Knoxville, Alabama. So a super small town of about 126 people. It's probably less than that now. So I guess really for me, I was raised in a super small town in the middle of Alabama prior to moving around and doing the graduate school stuff and whatever. I also like music, but I haven't played my guitar in a long time since starting as an assistant professor. I say that much. Like it was said earlier, my core research topics kind of fall in a few different areas. One being robotics, and this is also an image here from that first public brain drone race here. So I'll talk a little bit about that in more details later. So robotics is one research area that we like to focus on. Also here, this concept of human-computer interaction. Most of our work, this really serves as an overarching umbrella of where all of our work falls into. And so a lot of the objectives and outcomes that we look to present to the research community will fall under the umbrella of human-computer interaction. And this image here was just an early example of one of my first projects under the advising of Dr. Warren Gilbert at University of Florida of a system called televoting. So if you want to know more about that, you can just search televoting Chris Crawford, and that was one of my earlier projects that really focuses on the HCI aspect. Here's another aspect of this really weird picture that I usually do a short Q&A here to ask people kind of why would we be focusing in on tongue detection. So this was an earlier project where, in collaboration with DreamWorks and Intel, we were looking at ways to detect tongue protrusions. And this eventually, some of this technology, or I guess you could say some of the inspiration of the technology, ended up landing in one of the latest iPhones. So now in the latest iPhone, you can kind of get these facial features, and these little animojis will then mimic you. And so this was some of the earlier work that we did. But that work started in 2015 and then eventually made it into our phones. This project initially between DreamWorks and Intel was actually really focused on an application where Toothless, this character that was featured in this How to Train a Dragon movie, would then mimic your facial expression. So this is kind of how I really got started in the area of human-computer interaction. All right, so we talked about robotics, and then we talked about human-computer interaction. The other kind of main core of our research is brain-computer interfacing. And this is basically the concept of being able to measure in our case, electrical signals from the brain, and using software to try to make some sense of that. And a great deal of the beginning of the talk will be focused on kind of breaking that down and then building on it based on how the directions we're taking with our research. All right, before I start this, for those of you who may have may be unfamiliar with brain-computer interfaces, I like to show this just in case it can give you an example of where you probably saw it first.
The microbots are controlled with this neurotransmitter. What I want them to do?
So, you probably saw these clips and maybe even other clips in movies that really play around with the idea of being able to measure information, measure thoughts, if you will. We can't really measure thoughts. I'll talk more about that. But a lot of movies play around with this concept of being able to interpret things from the brain, right? Just using some type of technological interface. Oftentimes, you may think that, oh, this must be a relatively new thing, but this research has actually been around for quite a while. And this is a video from the 70s or early or late 60s.
This is nothing more than a light being turned on and off, a perfectly ordinary operation, except for one incredible thing. The light is being turned on and off by this laboratory technician. She throws no switch. She pushes no button. She's doing it strictly with brain waves. This is Dr. Edmund Dewan, an Air Force physicist who has been working with brainwave ideas. Dr. Dewan, exactly what is a brainwave?
Well, apparently the brain, in doing whatever it seems to be doing.
Right, and so I like to stop at that point in that clip because although we know more about the brain and its functions, a lot of us still have these same types of responses when asked exactly what the brain is doing, and it's, you could say like maybe 40 years later, right? Okay, so it's been around for a while, but exactly kind of how does it work? So super high level, a brain-computer interface starts by measuring the electrical activity from the brain. So you can have a headset. Sometimes the sensors are embedded in caps, but in general, you have what we call electrodes that measure electrical activity from the brain. This usually comes out as raw signals. And so you can see here, each of these lines could represent one location in the brain, or one electrode, or one channel. And over time, the electrical activity changes, fluctuates. All right. But looking at these fluctuations or changes, we can start to interpret exactly what kind of states users could be in. Okay. And this is an example of one of the headsets. One of the common methods of doing this is called electroencephalography, or EEG, and this is the method that we use a lot with our applications. After you collect the raw signals, you can then use software to actually extract what we call features, and then use those features to translate this activity into some type of command. So you can imagine this as getting a source signal, passing this information to, for right now, for the sake of this talk, a black box operation, output a command. That command can then be routed to an application. That application could range from a clinical translation application, a gaming application, a user state monitoring application, or in our case, we tried it with a brain robot interaction application. And I'll talk specifically more about that one later in the talk. Before we start to go too deep into the application side, I think one other thing is kind of good to understand almost as a baseline is the idea of, well, if we have these raw signals that look like this, exactly how can we even begin to start to make sense of this information? And one way is to actually separate these into different frequency bands. And so a common thing to do is to separate these across frequency bands labeled as delta, theta, alpha, and beta. And, just visually, if you start to inspect the differences in these waves, you can see this has a much less volatile behavior than the gamma waves, right? And so along with the signal characteristic change, previous research has informed that oftentimes these different signals indicate different types of potentially behavioral responses. So in this case, in delta has been associated with things like deep sleep, right? If you go up to alpha, one of the more common and popular ways of potentially detecting if someone is mentally relaxed, and all the way up to gamma, that's oftentimes looked at as someone is moving, and that's causing the muscles to actually send noise to the signal, or even some more recent research has been looking at the idea of, if you see gamma wave, this could be related to some type of heightened sense of cognitive processing, all right? And everything in between. This is just really high level stuff just to kind of get your feet wet with exactly how do we take a brain signal and convert that to something that could be even remotely used as some type of control signal. All right, so And when you put all of those things together at a very high level, you have what we call a closed-loop brain-computer interface system, right? Get the source signal, make sense of it, get features, translate that into a command, and then the last phase oftentimes is to provide the user some type of feedback. That feedback could be audio, it could be auditory, visual, haptic, but just as long as you provide them some type of feedback, then we can call that a closed-loop brain-computer interface. All right, so I talked about brain-robot interaction, and it has, I guess, various definitions, but I like to kind of just frame it as the study of interactions between the user's cognitive state and the robotic system, all right? And so if we can measure things from the brain to interpret a user state or user intention, and we have a system that then sends that to a robot, and then that robot can then intelligently respond, then we have what we call a brain-robot interaction use case. One of the, I think, common methods that was used early on is this idea of in the medical domain, if someone had a physical impairment, whether that be through arms or other limbs, then you can actually bypass the central nervous system in order to control that neuroprosthetic or that robot, in this case, instead of the user having to use a physical limb. This is actually a very key point in the history of the research, because a great deal of the research in the past and even now is inspired by these use cases. And so this area is very, very important. In our cases, we wanted to look at different control paradigms from a control perspective. And so to break down this, I want to kind of go over the high-level different paradigms that exist. And so one paradigm is actually called active brain-computer interfacing. And so in this paradigm, the user is actually intentionally trying to move an object, right? They're using the system with the active intent of moving a system. This is a video of the first implementation that we built back in 2012, I want to say, of a drone moving. This is we weren't the first to do it. I want to say Minnesota was the first to actually present this work. This was our first implementation of it in 2012. All right, here we go. I'm gonna play it. So in this case, my colleague over here was actually mounted with the headset, but this was a weird case because I actually forgot to add in the manual override so that I could actually make the drone not fly into this forest. But he was actually able to cognitively make it turn around in this case, in that one case, right? And so in this case, this gave us confidence that maybe it's at least responding to one command, right? This is an example of an active control paradigm. In a passive control paradigm, the user is actually not intentionally trying to send a command to the robot. Instead, the robot is just implicitly responding in a passive manner to the user state. One of my colleagues here in 2012 presented work where this robot would start to use gestures to get a student's attention when they notice their level of engagement dropping. And so in this case, the information that was collected from the EEG device was actually just mapped to different gestural behaviors of this robot. And that's an example of passive. So in this case, the student wasn't actually sitting there trying to intentionally make the robot move, but instead the robot was just really adapting and responding to the passive collection of data reflecting the student's behavior. Another core one is, actually I have a video. I think let me see if it's a play. So someone on this call is actually from SAP, so not sure if you're aware of this video, but this is work from SAP and Motive that looks at kind of a future version of what passive BCI may look like in the workplace. play a full video, but in this case, this was a potential use case of the user working and the system detecting that they have high levels of stress and they should maybe take a break, right? In the real world, it probably wouldn't work exactly like that, but this is just kind of one conceptual video showing how it could work. Okay. All right, and the last paradigm would be reactive brain-robot brain-computer interaction, which in this case, when certain stimuli in the external environment occur, in particular visual stimulus that's flickering at a certain rate, when this occurs, the brain actually responds in a very, I guess, predictable manner. And researchers early on, I want to say in the 80s, definitely in the 80s, figured out a way to actually use that information in a closed loop manner. One of the most commonly used ways is to implement a BCI speller. So let me play this video. So in this case, each of these letters are flickering at a different frequency, and the system, the brain-computer interface, will basically be able to indicate which letter you're looking at based on mapping the frequency values to a predefined letter that's mapped to a predefined letter. So in this case, the user was looking at E, and so the keyboard could know to select E. And in this case, you could have basically a hands-free keyboard, which again could be very useful in the case of someone who may have a physical disability. Okay. So those are the main paradigms. So this is kind of where we were with the different control architectures at a high level, but from I guess a system side, which is what I like to focus on, there were multiple gaps that we found early on in the research when I first began my graduate studies. One of the gaps was that there was a lack of work specifically investigating modular brain-robot interaction structures. This idea of modularity is a common thing in computer science and in specifically robotics with the introduction of a system called robot operating systems. But there wasn't a lot of work explicitly talking about research that falls at the intersection of this focus of modularity in robotics and this focus of brain-computer interfaces. And so this is something that we started to do early on. I think another key thing about what we were doing was this idea of early on investigating how we can leverage modern web technologies in order to address some of the gaps. And so overall, we've seen this very, even in the last, I want to say, decade, prominent progression of brain-computer interface hardware. So if you see this image at the top, it kind of shows you some of the earlier devices from Hans Berger, who discovered the alpha wave and EEG, all the way to like 2014, where you have this headset, this kind of nice looking sleek headband. And actually they're kind of selling it as a consumer device now. So if you go and Google this, you're going to get a ton of ads about buying one. And so although the hardware has progressed, the software is not so much supportive of different applications that may go beyond the out-of-the-box experience with these hardware devices. This is an example of an application we built connected with modern web technologies, and in this case, we're actually using the EEG device very early on. This is like 2012 to actually control things across different web platforms, right? And because we were focusing on modularity, this allowed us to rapidly prototype different brain-computer interface systems and test them out in more real-world examples. This is a high-level idea. I'm not sure how many of you are familiar with NodeJS, a framework, but this is one of the modern web technologies we started early on to build on top of with our brain-computer interface applications, and so it allowed us to build these multi-users, cooperative, or even competitive interactions. A cooperative use case would be, let's say we have two users that wanted to control this robot. The reason why you want that is because the output of information that you can get from one user using a BCI device could be constrained, right? But if we split the cognitive load between two people, then maybe we can see some advantages at the expense of more manpower. So in this case, one user was responsible for making the robot go forward, and the other user was responsible for making the robot rotate clockwise. And so you see this rotation, that's the second user, and then the first user can take over control when it's time to go forward. This was something that was inspired by a previous study that NASA did to explore whether this type of control could present advantages in an outer space environment where hand mobility may be restricted. Okay. Another thing that you can do that we found out really interesting is we can take these levels, this information from EEG data to measure, get a sense of engagement. That's very disputed. I get a lot of questions on that. But we can take it to try to interpret engagement. But in one case, we actually applied a heat map to see if there were differences between using it solo, so just one person using this control versus spreading the load across two people. And just looking at some of this visually, you can see that at least in this one case, we saw differences across the solo condition and the cooperative condition. All right, let's talk about competitive really quickly. So in the first case, I talked about two people sharing the load. That's more of a cooperative interaction. One of the things that we started to explore was competitive brain-computer interface applications as well. And this was the first example of it that we could find. I'm pretty sure there's older examples, but one of the popular ones was in 2003 with this application called BrainBall. Now you may have seen this as a product called MindBall, a MindWave. It's actually like a toy marketed towards I guess kids. But early on, researchers from Germany in 2003 first presented this idea of having two users of a brain-computer interface actually trying to control the interface that was framed as a competitive experience. And in this case, the users sat across each other and they actually tried to, for lack of a better word, out-meditate each other. So because we can measure the level of relaxation, we can use that information from two separate users as a control input to an interface and set it up as a competitive application. So in this case, the more relaxed the competitor is, the closer this ball moves towards the opponent goal mouth, if you will. So that was a really interesting one that inspired some of our later research. And so what we actually did was we combined this with controlling like drone racing, right? And so this is an image from 2019 at the University of Alabama where we did the second one. The first one was at the University of Florida, and one of the things that changed for us in this case was that we were no longer in a controlled lab environment. It is not easy to do it in a controlled lab environment, but it's much harder to do it in an environment where you actually invite out the entire university and the local community to come and watch people actually try and attempt to control these interfaces. In particular, because we have like drones flying around, you see that we have protective structures around it to make sure that the drone, if we do have an issue, doesn't go past the barriers and hurt one of the onlookers. But we also had to tie in constraints in the system to be able to completely shut off the system if one drone goes down. And this was also a testament to actually having people trust and be aware of this type of technology. So for the first time, a lot of folks from the local community came out and learned about this new emerging technology. Okay, that's just more stuff. This is a video from after we did the first brain drone race.
It said you can do a lot with mind over matter. These students are putting that theory to the test. They're using their brains to control these drones in a unique race at the University of Florida.
All right. right? And so this work in particular, you know, got a lot of headlines, but in particular, it inspired a lot of like high school students to email me and want to know how to build their own, and it just inspired a lot of young students to know more about this technology. And we saw this as an opportunity to actually engage them in it. But the first question was exactly how can we turn this kind of really complicated layers of signal processing and classification to something that a student can just walk up to and engage with directly. And one of the things that we built on was this idea of block-based programming using primitives as puzzle pieces, which there had been loads of previous research on this. Many of you are probably aware of it, that showed that at least for, you know, getting a student started and introduced with a concept, this could present a potential promising opportunity. Jury is still out on, you know, at what point do they need to transition to more text-based approaches, but at least for that initial interaction, this has been seen as a promising approach. So in the introduction, you heard the mention of Neuroblock. This is one of the latest systems we're working on. Neuroblock is a completely web-based approach to it. All you need is one of these devices and a web browser, and a student can start to build their own brain-computer interface. This is one of the earlier images from it, and this is a general idea of kind of how we were using, again, modern web technology such as NodeJS to connect these systems in a very short amount of time, thanks to a couple of Google developers. This tech stack became very, very light, if you will, in comparison to what I had to do when I started in the good old days, if you will. And so this idea of browser-based solutions for Neuroblock, I want to say we're one of the few labs in the world working on it, but we're seeing definitely a good progress on it. This is thanks to a tool called BCIJS that one of my students, Pierce Stegman, created. So if you're really interested to learning exactly how to start to build your own systems in the web browser, definitely check out BCIJS, one of our projects. You can just Google BCIJS and it should come up. And this is also a pretty informative blog post that one of my students wrote with getting started with the idea of motor imagery classification, basically being able to detect if someone is imagining moving or activating the limb, and then converting that into a command. And this was hosted by a blog called Taurus Data Science. And this is some stats on BCIJS, so you can look up that more. As I close, when we reflected on brain-computer interfaces in general, we've seen a consistent theme that made sense. It was that to get really, really good, high-resolution, accurate predictions on cognitive commands, you've seen a consistency of having a bunch of electrodes. Now, while this interface could be really good in cases where you just want to get the data, you want to post-process it, you want to move the needle on fundamental science in the area, it could present barriers when you want to, say, take it outside of a control lab or introduce younger students to the technology. And so that was one of the things that we recently looked out towards addressing. And so I want to show you a video that I think was this is what inspired me to continue to do this work. This video was taken from a science expo in DC, and it was sponsored by the National Science Foundation. These students, we gave them like 2 minutes of introduction on what brain-computer interfacing is. I'm assuming they had already been exposed to Scratch, so they were familiar with how to go ahead and manipulate the blocks. And so in about 5 minutes, these very young students began to make their own brain-computer interface applications. And so for me, especially, given, times like this, I wanted to focus on to make sure that these students that look like me weren't necessarily the last to learn about this type of technology. So this video is very dear to me, and I'll try to narrate it for you. So basically, the student in the white shirt is what we call the driver, and he is going to be building the application and giving instructions to the actual brain-computer interface user. So at one point in this video, he's going to tell his friend to close his eyes and relax, and I'll tell you why this is really important in the next slide. So a couple of things are happening in this video. One thing is that the student is being engaged in a STEM education activity, right? And this is nothing new. This has been, studied for years. But the second thing that's happening that's really interesting is this idea of peer-inspired mindfulness activities, all right? A couple of years ago in Baltimore, a few schools started to try to replace detention with meditation and mindfulness practices, and they saw some promising results. And so one of the things that we're trying to explore now is we're trying to see if there's an interesting link between computational thinking activities and also mindfulness practices. We want to see that if we can start to also engage students in not necessarily learning the computing side of it, but also these activities that could potentially, far in the future, influence some behavioral outcomes. This could be, to my knowledge, one of the first times it's been actually discussed. If you want to learn more about that work and kind of some of the things that we found out in that preliminary study, we published a very preliminary article at CHI in 2020, and we also published last year more details on the Neuroblock system and the transactions of computer education. So if you want to just kind of dig into the weeds and get more details about that. So with that, I want to show a few of the students that graduate students in the lab, and peers, and Ajay and Shamare were students, and I have many more, but I'm still waiting for them to send me all their headshots. So. But with that, thank you. And I guess this will be a time to open for questions.
All right, thank you, Chris. We did have one question in the chat from John Coleman.
Okay.
Let me see. John, if you're out there, you can come off mute and ask it yourself.
Hold on, can you hear me? Hi there.
Yep.
Okay, so I see that you talk about the difference between when you do these experiments in a controlled lab versus doing it in a arena like a robot competition. Do you have to build any kind of Faraday or blocking mechanisms so that you can maintain a clear playing field?
In the ideal scenario where you had the budget, right, to do it, and even the time, I think having any type of apparatus where you could have, it would be two things you want to consider in that case. You would want to be able to control to make sure any type of electrical signals or noise that wouldn't necessarily be filtered out with normal pre-processing methods. You would want that to actually be in place. We didn't do that because of lack of budget and time constraints. But the second piece is, because the focus was not so much of only, getting the best and perfect signal. That was one of the constraints or one of the design top design considerations. The other thing you would want to do is to make sure that whatever barrier you had, that the onlookers wouldn't be impeded to see what's actually happening in that case. And so in particular, when we talk about you know, like a larger part of not so much of only pushing the fundamental science, but also looking at this idea of how did you have like social interactions beyond that one user. You have to think about those type of design considerations. But this would, as we progress, this would definitely be one of the things to ensure that it's not fair, that is not unfair to the competitors.
Okay, and then the last part of my question is around the idea of at what age bracket do you find that you're able, that what's the youngest point is too early to just try doing this kind of training, and at what point is the mind not capable of doing these kinds of exercises?
Sure, great question. So in our existing study, we are starting with 11th and 12th graders because we were building on an existing program that already introduced students to some of the Scratch concepts, right? So you had 11th and 12th graders, and this was just really because we were building it on top of an existing Scratch course that taught them the fundamentals of that. But if you look at some of the things where we start to look at some of the fundamental things about signals that come in, about algebra and some of the things in sine waves and cosine waves, I think there is an opportunity to start to introduce simple, basic concepts of like, oh, this is a signal. Okay, this is how we can kind of look at this signal. This is how this type of math concepts are mapped to that. And that could start around 8th and 9th grade, but we haven't went down to that level yet. Part in because we don't want to like present a cognitive overload to a student that has, number one, hasn't programmed before, and also has no idea how these signals are coming through. So the short answer to that question is we're really not sure yet, because the work of looking at students really below graduate level learning these type of concepts just don't quite exist.
Sounds like you got a research.
Yeah, I'm actually funded to do it now. Yeah, so yeah, I do actually. So thanks to the National Science Foundation, all of the work that I presented to you at the latter part of that was funded through the National Science Foundation. Great questions, though. Thank you.
Okay, so we have a few questions in the chat here.
Yes, I didn't. So in that paper. So I'm looking at George Wilkerson's summer camps. So last year we did the first NeuroCamp, and NeuroCamp was basically a camp where students came and learned how to use Neuroblock. And that paper that I presented, which one of these? The one that just came out, Changing Minds, Exploring Brain-Computer Interface Experiences with High School Students. It talks about that summer camp and results from that summer camp. I should note that also this study was really focused on exploring students from my hometown, which is 99% black. And to our knowledge, this was the first time that researchers actually focused on how our community perceives brain-computer interfaces technology. So in particular, how our students perceived it, and that was one of our goals, to figure out insights on if we, in the future, if we want to design these types of systems for students in our community, then how do they look and how do they perceive them? So some of the preliminary outcomes are in that paper if you want to know more about that one. Notable distinction, BCI capacity and age groups, if any. So I'm looking at Samuel Nixon. How did you find notable distinctions in BCI capacities between age groups, if any? So that wasn't that wasn't necessarily linked to any of our core research questions, but anecdotally, we saw differences. We just noticed differences in younger students' activity, right? And that's all I can say. Like, the younger students had higher levels of activity. So some of those higher frequency bands we saw higher levels of activity. This wasn't something we studied. We didn't run it through any type of statistical analysis, but that's something that I do plan to go back and see how that influenced our results, if at all. Okay, is there a possibility in detecting BCI opportunities in communities of different cultures? So a lot of the, and one of the reasons why I do what I do is a lot of the previous research doesn't necessarily look at the intersection of different cultural communities and BCI. The one line of research that I am aware of that my colleague looked at, Franz Jackson, is the idea of how hair influences reading the signals. And so that's one of the things that she looked at, and you can just Google Franz Jackson. She looked at that. But as far as kind of anything that looks at the intersection of like cultures and BCI, that work is also very limited. Okay, I think someone was jumping in. I'm not sure if we're running out of time or not.
Yeah, how you doing? My name is Lawanza Quince. Can you hear me?
Hey, yeah, I can hear you.
Hey, how you doing, man? Hey, I'm a .NET developer. I build, systems, doing some work at Abbott and working for the state. Was wondering if possibility. I have a background in chemistry, chemical engineering, so a lot of hands-on experience. Was wondering maybe we can talk offline and collaborate on some projects. I won't say what school, but I'll be going to a real top-tier school in the fall to finish for a master's PhD program, and maybe we can connect.
Definitely. I'm not sure if I dropped my email in, but you can look it up. Definitely. Yeah, here it is. Send me Crawford@cs.ua.edu. Definitely ping me. Let's talk offline.
Okay.
And congrats.
I don't. Repeat that again.
I said definitely you could ping me offline. We could talk in more details about specific collaborative opportunities. And I said congrats.
Oh, yeah. Thanks a lot. Yeah. We can do that. Thank you for answering my question, Dr. Crawford.
No problem. Okay.
See a few more in the chat, and also Sam asked if you could put the research paper information back up on the screen.
Oh, yeah, absolutely. These are the latest two.
Looks like John Coleman asked about the intersection of gender.
Yeah, there's definitely there's more work that looks at gender. There we go. I see it. There's more work that looks at gender. In particular, the work that we were looking at the University of Florida with just kind of the source signal acquisition differences. That specifically looked at her dissertation was focused on how to design fashionable brain-computer interfaces for women. Okay, and so that's one of the author is Franz Jackson from the University of Florida. That work specifically gets at the heart of it with the focus of looking at women specifically. A great deal of the other papers would look at gender more for behavioral outputs and not necessarily control outputs, which most of my work focuses more on the control and not necessarily directly influencing the behavior. I hope that kind of gets you in there. Oh, I'm sorry. I went back over here. Let me put this back up, though. I just noticed I can't look at the questions and and have the paper up at the same time. So this is the paper again. I'll leave that up for a few seconds before switching back to the questions.
Okay, and I can read through this. And Lawanza, I see you message me privately. If you click that arrow and click Chris's name, you can send that message to Chris directly, and he can see it with your contact information.
Thank you for pointing that out. I didn't see the name. All right, then.
No problem at all. No problem. Right. Had a question in here from, this is asking for your contact information. All right, so let me put your email in here. And Chris, if you can just call it out, I think it's what Chris
Yes, Crawford. CRAWFORD at CS.ua.edu.
.edu. All right. Oh, sorry. I sent that to directly. All right. Let me copy that again.
Switch back over to see. Could you? Thank you.
There we go. All right. I just put Chris's email in the chat. I will unmute the lines at this time in case anyone else wants to come off of mute and ask a question and is having challenges doing that.
Carl Hill.
If you're not speaking, I would ask you to mute your line.
Hello, this is Carl Hill. Can you hear me, Dr. Crawford?
Yes.
Just have a question regarding the social well-being of the students, whether or not you've been able to determine whether or not there's a baseline difference between any of the kids who are going through any dysfunctional issues at home on whether or not they have difficulties getting into the mindfulness in order to be successful in managing the drones. And if so, do you guys have anything in place to kind of help them manage through that?
Right. That's actually more in line with a proposal I'm actually in the process of preparing, right? And the one thing I would say, I would point you to some recent work by Dr. Marvin Andujar, one of my colleagues at the University of South Florida. And he focuses more on looking at behavioral variables and how we can leverage EEG to start to investigate those things. I'm not sure if you can hear me. I think somebody muted. That's my first point. That's my first point on that. There is previous research by some researchers in Canada. I want to say they were also published at CHI. That look at that. If you want to ping me, I can send you some papers that I've been keeping a watch on in that area. So I guess my short answer would be that there's researchers looking at it. We haven't really explicitly framed our work around it yet, but that's definitely the direction we're going in now. Since we created our initial prototype and we know that students will engage with it. So now the concept is, okay, how do we refine our design to actually start to affect some of those behavioral variables?
Yep. No, I will definitely send you an email. I'm very interested
on that.
in some of the work that we're trying to do as well, especially with a lot of the dysfunctional homes and the kids who may have experienced some ACEs. And and there are some things that if they are really become passionate about doing something, then I think we have the ability to kind of drive them differently from, to accelerate trying to do some of this. So I'll definitely send you an email on that.
I definitely have multiple links I think will be very relevant to that, because I've been paying attention to it for the last 2 years. In particular, you could just look at the things that the Baltimore schools started to do with replacing detention with meditation. I think that would be a good start. This was not necessarily peer-reviewed research, but this is what kind of turned me on to the idea of understanding if we could start to use EEG as an objective measure to start to serve as a way to drive these behavioral outcomes.
Very, very good. Thank you, sir.
All right, thank you.
All right, Chris, we got 2 more questions in the chat, so I'll ask these and then I'll close us out. Okay. So the first one is from Renetta Brown. I hope that's your last name. Yep, Renetta Brown. The question says, is there any ethical monitoring agency of this research? I'm glad you're in it, but I can see some pros and cons with it.
Yeah, I think the ethical monitoring agencies are going to be your standard ones, like your IRB and anything that's connected to the National Science Foundation. I definitely agree that with all innovations, you could definitely turn it into a negative outcome. But to the best of my knowledge, you're going to have the same institutions such as the IRB and any other additional one that may vary per institution. I know our institution is really strict, so it was very hard to get this research approved. If that, I don't know if that's a good or a bad thing. In this case, it's a good thing, right? Because there are people really asking a lot of questions about exactly what type of methodology you're applying, exactly what you're trying to look at, and why you're trying to look at it. But I would say that with the progress of this technology, and you have things like HIPAA in place, I think this will, and I'm one of the researchers who's actually advocating for doing things such as never storing raw EEG data on a server, right? So I have another paper out, that's a review paper on brain-computer interfacing systems, and towards the end of that, we start to look at this, talk about this concept of it becomes very dangerous, potentially, if you're just storing raw data on a server. So I look at it as, what I'm doing is providing design insights. Anytime we talk about how to build a system, we try to add in what not to do with the system because of potential ethical concerns. And that's something I've been vocal about and will continue to be vocal about.
Okay, last question is from Susan. And her question is, are you conducting studies with individuals that have diminished brain capabilities, such as dementia? If so, can you suggest any studies?
We're not working in that area. So for right now, we are really focusing on just the general population of students that may appear in a high school CS course. Currently, we are not using those types of. I'm collaborating with researchers who are. So, Dr. Even Malaya at the University of Alabama. If you go to our my lab website htl.cs.ua.edu, you can read a little bit about that specifically on ASD. I'm really just kind of backing her up on the CS and system side. But the core of my research kind of falls outside of that area.
That's not what I want to do.
That wasn't the question? Oh, okay. I hope I answered the question.
Yeah, I think we got somebody who's just not muted.
Okay. All right. So, yeah. But definitely, for more information, you can, I guess, follow me on Twitter, I guess, for the more recent things, but also check out our lab website, htl.cs.ua.edu, to kind of see a general overview of some of the other projects that I didn't necessarily have time to talk about on this call.
All right. Well, Chris, I want to thank you again for sharing with us today. This was super interesting to me. Definitely look forward to staying connected and seeing what opportunities we have to maybe partner on some things and get more youth exposed to this, because I think this is one of those ways of the future that we need to have people knowing about. So thank you for sharing with us.
Absolutely.
Lastly, I just want to remind you all to go to BDPA2020.com. I'm registered for the national conference, which will be in August. It will be virtual. I apologize for the crying baby in the background. It's a little over a month old right now, so bear with me. But I encourage you all to go register for the national conference. Our theme is Diverse IT, Digital and Transformation. We will be virtual this year, but we still will have some powerful content there. And also encourage you to look Chris Crawford up on LinkedIn, connect with him, and continue to follow his journey and what he's doing. Thank you all for joining. Have a great weekend. Stay safe, and have a good one. We'll talk to you next time.
Thank you. See y'all.
Thank you.